Hello, class. Now we're going to discuss light refracting. In general, light slows down somewhat when traveling through a medium. And the index of refraction of the medium is a ratio of the speed of light in a vacuum to the speed of light in that medium. So in a vacuum or air, the light can travel at the speed of light, but it will slow down through other materials like diamonds. Now light changes direction when crossing the boundary from one medium to another. This is called refraction. Angle theta 1 is the angle of the incident ray that makes with the normal and is called the angle of incident. Angle theta 2 is the angle of refraction, and the angle the refracted ray makes with the normal. Now notice that the ray bends towards the normal when entering water. This is always the case when the ray enters a medium where the speed of light is less. If the light travels from one medium into a second medium where the speed is greater, then the ray will bend away from the normal, as shown in figure B. Refraction is what makes an object half submerged in water look kind of odd. For example, a person standing in waist-deep water appears to have shortened legs. The rays leaving the person's foot are bent at the surface, and the observer's brain assumes that the rays have traveled in a straight line, the dashed red, and so the feet appear to be higher than they really are. And then similarly, if you were to put a straw in water, it appears to be bent. This also means that the water appears deeper, or is deeper than what it appears. Now the angle of refraction depends on the indices of refraction, and is given by Snell's law. Theta 1, or theta A, is the angle of incident. Theta 2, or theta B, is the angle of refraction. N1 and N2 are the representative indices of refraction in the material. For exercise C, we have a light that passes from a medium with N, which is water, of 1.3, into a medium of glass, which N is 1.5, and is the light bent towards or away from the perpendicular to the interface? It is towards because the light slows down as it enters a higher index of refraction and when it goes from water to glass. Now here we have a light traveling in air and it strikes a flat piece of uniformly thick glass at the index of angle of 60 degrees. If the index of refraction of the glass is 1.5, what is the angle of refraction, theta A, in the glass? And then what is the angle theta B at which the ray emerges from the glass? Now the first step is that we'll start off with Snell's law. Then we'll rearrange the equation to solve for the angle of refraction in the glass, which in this particular case it's theta A. From the index of refraction table, for air it is 1, and then for glass, which is given, is 1.5. And we know that the angle of incident is 60 degrees. Plug and chug to get an angle of refraction in the glass to be 35.3 degrees. If we were to use the same equation except solve for the ray emerging from the glass, we would get to no surprise of 60 degrees. Now we know that if light passes into a medium with a smaller index of refraction, the angle of refraction is larger, points away from the normal. Now there is such an angle of incident for which the angle of refraction will be 90 degrees. This is called the critical angle. Letter K is an example of a 90 degree of angle of refraction because the angle of incident is at the critical angle. Now, if the angle of incident is larger than this, no transmission occurs, and this is called total internal reflection, as shown at letter L. Now describe what a person would see who looks up at the world from beneath a perfectly smooth surface of a lake or a swimming pool. Well, if we were to solve for the critical angle, we would get 49 degrees. the person would see the outside world compressed into a circle whose edge makes 49 degrees angle with the vertical. Beyond this angle, the person would see reflections from the side and bottom of the lake or swimming pool. Now for binoculars, they're often used total internal reflection, so that this gives a true 100% reflection, which is even better than the best mirrors can do. Now the total internal reflection is also the principle behind fiber optics. Light will be transmitted along the fiber even if it's not a straight line. An image can be formed using the principles of small fibers.